I forgot to turn my microphone on, so I'm just going to have to narrate this. We'll see how it goes. It's not going to be live narration anymore. It's going to be narration after the fact. So in this problem, we have a insulating sphere. Positive electric charge is uniformly distributed, so the charge density is constant throughout the sphere, and we're asked to find an expression for the electric potential. That means we're going to want to find the electric field, and from the electric field, we'll use a line integral of the electric field to find the change in electric potential from infinitely far away, where it's 0, to a finite value, positive value, as you get closer to the positive charge. The volume charge density is just the total charge Q over the total volume, 4/3 pi, excuse me, 4/3 pi capital R cubed. So how are we going to find the electric field? We can use Gauss's law, or will we need to do an integral that adds together all of the components? So I'll start the clock. I will skip the clock parts, probably cut that all out. So here's the answer. Most of you say, by far, a large majority of you say Gauss's law will work, and that's exactly right. It's a spherically symmetric problem, and so Gauss's law is perfectly made for this. Not just a spherical object, but the charge density is uniform. So the charge density itself is also spherically symmetric. And so you can put a spherical Gaussian surface of any radius you want to. The sketch, the dotted line I drew there, was for a radius that's larger than the sphere itself. Positive charge again, so the electric field is the same everywhere, the same magnitude everywhere on the Gaussian surface, and it's perpendicular to it's parallel to dA everywhere on the Gaussian surface. So the left-hand side of Gauss's law is easy to do, and the charge enclosed is fairly easy to do also. You just need to integrate over the volume enclosed, the charge density over the volume enclosed. And you can do that with this Gaussian surface inside your insulating sphere, or the one that I drew outside, or draw a Gaussian surface wherever you want. As long as it's spherical and centered on the center of the insulating sphere, then you'll be able to use Gauss's law fairly straightforwardly. Once you have the electric field, and you know that it's radial, then all you have to do is, to find out differences in voltage, is integrate E dot dr, since it's radial. Integrate E dot dr to get a voltage difference.